welcome to NASA's VIPER Moon Rover Robot Build Watch Party. My name is Lara Strife, and we're taking you behind the scenes for a live exclusive look at our VIPER rover as it's being built.
And I'm your co-host, Mia Blessing, and we're coming to you live from NASA's Ames Research Center in Silicon Valley, California. Joining us today in our studio are VIPER mission experts who are going to be hanging out with us, watching the build, and answering your questions.
Let's meet them. We'd love to have you introduce yourselves, so why don't you tell us your name and what you do for the VIPER mission. Ryan, let's start with you.
Yeah, I'm Ryan Vaughan. I'm the lead mission systems engineer for VIPER, which means I'm overall responsible for the success of the mission, make sure that the rover does what we need it to do once we get to the surface of the moon. I'm excited to be here again, so thanks.
Very excited to have you. And Emily, how about you?
I'm Emily Mcbryan, and I'm the technical lead for the environmental covers that go over VIPER, and I'm also 1 out of the 10 VIPER drivers. Thank you for having me.
Such a cool title.
Well, thanks so much for coming out and hanging out with us today. Around here at NASA, we love acronyms. So, Ryan, can you tell us what VIPER means and a little bit more about the mission objectives?
Yeah, so VIPER stands for Volatiles Investigating Polar Exploration Rover. As it sounds, we're looking for volatiles, and especially water in this case. We're kind of like a resource prospecting mission. We are looking to map water as a resource, understand where it is, how much is there, in what form is it in. We have signatures from orbit and past missions that show us the signatures of water, but we really need to get down on a ground level and understand, in a working sense, where the volatiles are, where the water is, and it can help inform not just science on the evolution of water and other volatiles on planetary bodies, airless planetary bodies like the moon, but also in the sense of exploration, like can it be used as a resource, and it'll help inform future missions that would then be able to extract and process or store. So understanding where it is, how to get it, and how much is there to help us see the value of it. Anytime you can use a resource that's local, that's where already there
yeah.
for you, and you don't have to bring it from Earth, where it's really takes a lot of effort and mass to get it out into space. So if we can use it there, then it enables a lot more both science and exploration. So we're excited for this mission. It's a very unique mission, and nobody's ever really been to this kind of environment. No one's been to these crazy South Pole locations. So it's exciting to be involved.
Super cool and innovative, right?
Yeah, I mean, it's a historic mission, so how did you both end up working on it? Was that something that you were working towards your whole career, or did it come as a surprise? Is this a high for you?
Oh, definitely a high. The moon.
Yeah.
Always been a dream to work on, outside of the Earth, and the moon's always been there, just kind of taunting, always in reach almost. And I came from wearable robotics, and how mechanisms and robotics can work with soft substrates, and so being able to apply that knowledge for VIPER on all of its environmental covers, it's been amazing. And then also to drive the robot on the moon remotely. Who gets to do that?
How does one even prepare to become a rover driver?
We, even though the robot is not built yet, it's not complete yet, as you can see in the live feed, we've been testing and learning how to drive for this entire year with sims and simulations. We'll do mock missions in our mission control here at Ames, and we get the whole team together, and it's great. You run through problems, whether we plan those problems or not, and it's wonderful. So we're learning.
It sounds really fun.
Yeah, I think just one of the coolest things about this project and why it's so unique is the moon. Like you said, you can see it, right? You can. It's one of the few, space destinations that you really see all the time. You just look up and there it is. And you could just picture, as we've been working so hard on this, through the design phase and getting components built and finally starting to integrate, it becomes more and more real. And you look at the moon, and that's where we're going, right there at the bottom, in the South Pole.
That's so cool.
Yeah, it's a cool mission to work on, and have that connection with something that we all see every day almost.
Yeah, that's amazing. So why don't we go ahead and start checking in on our rover and see what's going on in the clean room? Take a look at what's happening. Can you tell us more about what's happening and what's being built and what we're seeing, these images?
Yeah, I can. Hey, Justin. So
some of your coworkers, you're saying that?
Yeah, I'm saying hey, Justin, hey, Nathan. What we have here, this is really exciting for me to see personally because I've been waiting to see this robot get the warm box installed. You could actually see 3 out of the 4 walls to the main warm box where we store all of our avionics. This is where it's the most environmentally controlled place on the rover. So anything that's really temperature sensitive, we have all the computers all tucked in by itself so that when we warm it, we can just really focus on warming and taking care of the center of it. So it's a huge milestone to be able to get all the electronics in close board. And so that's really the heart of the rover is in that box that's right there. And then it's, of course, sitting on a drivetrain chassis. And while it doesn't have its big wheels on yet, you can see 2 of the motor mobility units in the 2 sides. So it's like that's where we're going to mount the wheels. And look. And this is the last panel. So that I said we had 3 mounted, but here comes number 4.
Wow.
And I've been chuffed to see it.
Yeah, you can see we kind of have this panel pre-populated with a lot of the electronics that go on it. And all in the same fashion, all 4 panels have been built up this way. And it allowed us to kind of take a parallel approach to building up all the panels and checking out some things while we're getting all of them ready at the same time. And then when they come together like this, we typically do we just connected it for the first time together with the other components of the rover, and we get some power on testing with the vehicle in its configuration. This is exciting.
This is yeah, and we're really pushing towards like trying to get power on testing and as much data as we can. That's possible. Every time we take a step forward, we integrate more things together. We take a step, we process, we test, and we look for bugs, we look for issues. So it's been a long time coming to getting all the panels together, and it's really exciting whenever these power up tests happen.
Yeah. Sorry.
I was gonna just to ask. So then they'll put this up and they'll run some testing for it. So each one of the panels gets its own individual testing, and to make sure everything's working before you continue to build.
Right, and all the panels have been tested individually, like by themselves, and all the avionics and things have been tested before they were put on. But when you get into these larger system level testing, we have more pieces of the puzzle coming together. That's more possible for more issues that have unforeseen issues that come up. You gotta know what they are. You gotta tackle them. So it's a busy time.
Yeah.
Yeah. Well, it's great to hear that you guys are as excited as we are because, we don't always know exactly what we're seeing. This does look like it could become a rover one day, and it will, but it looks quite different from the rover that we have in front of us, our scale model of the VIPER rover. So what can you tell us about the parts that we're seeing right now and where they fit in with the sort of overall vision?
Yeah, it's a little hard to envision now, but if you can kind of see the model in the corner here, the outside, the solar panels that are on the sides, the radiators on top, it's what you see being kind of integrated here at the moment with the panels is actually buried. Well, it's not buried. It's in the middle. It's in the core of the,
like the
of
inside
the rover. Yeah. There's actually it's a little deceiving because there's a little space between the walls of the warm box and the solar panels. There's a lot of reasons why they designed it up that way, but so the shape gets a little different. With the wheels that Emily pointed out, you kind of see a sense of where the wheels are, so they come out. So where the wheels are in this and where the solar panels are in the model here, you might be able to envision like the shape. It gets a lot larger once you get more things on it. And those steps will be coming up soon. If we get all these 4 panels on, to get them all checked out, we'll probably be starting to get this larger shape being integrated pretty soon after that. So yeah, it's coming together.
It's coming together, and like Ryan mentioned, we have a lot of integration going on different parallel paths. So even though like we could only see the heart of the robot, which is really the coolest place to look inside the sieve, but behind this is the upper frame, and to the other tables as you could see some of the solar panels. So we could walk through and actually be able to pick out and see and visualize all these different components coming together to make what we see in like the final mock-up and final model.
Other cool things on this notable, you don't see it because it's not installed yet, but actually like going through the middle of the worm box in the picture and the whole rover is a drill. You see it in the model sticking up the top here. It's a 1 meter drill, and that we use that to dig up subsurface material so that we can see what's the content of volatiles and water in the subsurface, not just what we drive over. So the drill is an important part. Once you get all these boxes in there and closes, there's not a lot of room in the middle, but it's of course perfectly designed for this drill to go right through the middle, and it goes down pretty deep, up to 1 meter. It's and that was a driver that the scientists are really interested in, what's in that top meter. And they can explain it better than I can. But
it's fascinating watching them do stuff.
Yeah.
And my eye always goes to the shiny that looks like aluminum foil. It's not aluminum foil, right?
It's true.
Can you tell us more about the shiny piece of it, Emily?
What the shiny things is called MLI, or multi-layer insulation. It is aluminized, so it's where kind of you get that. Oh, is it aluminum? Like, well, it's vacuum deposited aluminum on like a thin mylar sheet or Kapton sheet. That falls into my wheelhouse because it's part of the environmental covers that I deal with.
Right.
So over the entire VIPER, we have 180 different environmental covers, or thermal blankets, or just MLI is what I call it, multi-layer insulation.
Yeah.
It's a lot. But I've got a team of great designers, and we basically just build up all of these clothes for the rover, and they're fully integrated because the temperatures are so crazy, and it's such a big part of the rover to be able to survive these drastic temperatures with our passive thermal system. So we have like this Russian nesting doll of MLI blankets and internal like thermal blankets and environmental covers, so that we can really insulate all of our, like the heart of the robot, all these electronics, all these avionics, to have a temperatured controlled environment, as opposed to like what's going on the outside with the big giant highs and the big giant lows when the sun shines and when it doesn't.
Yeah, one of the biggest challenges for this mission is the thermal environment. We plan to go into permanently shadowed regions, which is areas on the moon that have never seen sunlight for billions of years. It's a long time, like it's a geologic timescale. It's billions. And it's cold. It's cold in there, and so we're going in there, and we have to operate. We have to stay warm, but then we also most of the time actually operate in the sun, and we get pretty warm when we got all our electronics on.
Yep.
Things get really warm, so we have to handle both of these extremes, and so all these soft goods are designed very carefully and built very carefully by Emily.
Absolutely. Well, yeah, not just me. I've got a team of soft goods designers that I work with, and even like a master seamstress to actually like fabricate and get all these blankets designed, fabricated, and integrated. So.
Yes, if you don't have to be an engineer to work on a space project, you can be a seamstress.
It's
Absolutely.
a different kind of engineering, isn't it?
Yeah. It is, and it's also just a more artistic side of things.
Yeah.
And so, like, my background is aerospace engineering, and I was, trained on all those, like, all the CAD programs that we use, but all those programs are used to model and design, like, hard pieces of structure, very rigid. It doesn't correspond well to fabrics, and it doesn't replace any of like that more creativity mindset.
Oh, looks like it's going on.
Wow, that's cool.
Dang.
So you guys seem very excited about this too. If you were in Houston right now, Emily, would you be in the clean room for this process, or would you be watching outside?
I might try to say like, oh, well, as someone who does MLI, I should be here just to make sure you don't
Just to get in the room.
my things. But I mean, I'm not needed in
that's
this
so cool.
procedure. It is really cool to see it, and it's yeah, I'd try to whittle myself in or be right outside the right outside the window.
I think I would do the same. I totally understand.
So you get to go into the clean room daily, regular? What's like kind of the occurrence of that?
We've got like highs and lows. So like last week I was in there every single day putting in blankets and installs, but that's not always the case. It really kind of shifts on what is needed at the time. And with MLI and installations, it's whenever the hardware is ready, then we go in. So we really have these areas where we are super busy, we call them sprints, and there's times when we get a little bit more relaxed and I can come out and hang with you guys.
MLI is a really interesting one too, because it's you design it to a degree, but you really got to, get on the actual final thing that you need to actually finalize it.
Yeah.
So you have to kind of feedback.
And that's why I like having like a master seamstress is good, because you design this thing on a rigid body and then it's like, oh, well, this doesn't quite fit very well. So you have to learn how to like, oh, if I just take, scissors and cut here, that gets rid of the stress, and I can just repair it with, tape, and then it fits nicely.
Yeah, and you have some great stories about tape too.
Because when you're working on a mission as cool as this one, everyone expects you to be like, oh, I bet you're just thinking of the moon every single day, and you got this high-level picture. And I'm like, no, I actually just think about tape a lot. Like, that's my like day-to-day thing that I focus on, because it's what I use every single day. It's what I care about. Like, someone has to care about the nuts and bolts of this rover, and the nuts and bolts include
tape. Yeah, so we know to come to you if we have tape questions in our future.
Type of tape, yep.
Perfect.
Yeah, this is just tape you get at the hardware store, right?
Oh, absolutely not. No, we even have a custom design and fabricated tape by NASA, and there was one day when I was like about to do an installation, and someone's like, well, that tape expired.
Tape has an expiration date?
Yeah. Basically what I said. And I'm like, what do we do? Anyway, so we get more.
Yeah.
Toss it out.
Well, now I have to go check all my tape rolls.
I know.
Yeah, I never thought.
Especially with everything gift wrapping. Well, we've gotten some great questions in the chat and some comments.
Yeah.
And thanks so much for the engagement that's coming in. Why don't we take some questions from our audience?
I think we should. We got one in here about the rover. Will it be expected to scale slopes? What are the challenges of that?
Yeah, so it's designed so we set goals, we set requirements, and then it has a capability, and if you design it to meet the requirement, like, that can be good, but maybe it's a little too close to the edge, or we usually get performance that's a little beyond what we actually need it to do. But when we operate it, we also have to be a little more. We have to be cautious. We can't be getting too close to the edge. So we set our requirements for the design, and then design proves that through a lot of testing, we've done a lot of testing with the mobility system in flight-like simulant, and it shows that it can meet its performance. So it's about the requirement, and the limit that we set in operations is 15 degrees, which it doesn't sound like a huge number. It's actually, when you're on a 15-degree slope, I know skiers out there, right? It does feel pretty steep. So it's a pretty good capability. It's just a very there's some uncertainty in the environment, the soil, the properties, and how it will interact with the rover. That's why we do a lot of the testing that we do, just try to know as much as we can about the performance in the expected environment. But it's not the moon, right? It's not in 16G. It's not lunar, real lunar regolith. So we do the best testing we can in the analog that we can, and we gain a lot of confidence that way. But being able to achieve that, the mobility system for VIPER is actually, it's pretty unique, and it's designed specifically for the lunar polar environment. You can see it's a little different from maybe other planetary rovers that NASA's built in the past. That's intentional. The engineering is driven by the environment we're going to. So it's interesting. The two, they're harder to see now because the stuff's in the way.
It's in there, yeah.
The two wheels, there's 2 wheels on the other side too, so it's 4 wheels. So a lot of other planetary rovers have 6 wheels. We are 4 wheels, and each wheel has suspension, so each wheel can independently go up and down.
An active suspension, not just a passive.
Yeah, we do load
Important
balancing.
distinction, sure.
Yeah, we do load balancing, which is an important way to help maintain traction, and it helps with our ability to climb slopes.
Yeah.
And they also can independently, kind of rotate.
An independent steering.
Yeah, steering. Yeah, so they can we can put them in like a star configuration, which we do sometimes when we park and we don't want to move at all. We can crab drive, so you can, and we use that a lot because we generally want to keep our solar panels on the pointed to the sun. So if we can drive kind of in any direction and keep that orientation, that was intentional and part of the way you design, how much power you need and how much you get and how much you're using, how much you rely on the batteries. So it all comes together. So the mobility system has this capability, one, to reduce the chance that we get into a tough situation that we can't get out of, and also to be able to achieve these 15-degree slopes on uncertain terrain and regolith, and just trying to make sure that we can go everywhere we plan to go, because we have to control our traverses to not exceed that 15-degree limit.
Right, yeah.
So it's a constraint when we plan the mission based on the design. So it's been a
lot of testing involved, and even when we go up that 15-degree slope, I'm using my hand as an example, because we have an active suspension, we can just because we're on a 15-degree slope doesn't mean the rover's at a 15 degrees, because we can use our active suspension to put these wheels closer to the ground and these wheels higher, so that it really makes we're not going to have any risk of tipping over or anything bad happening, and so that we can also keep a good alignment of our solar panels to the sun. So that's just one of the capabilities that we can go up a 15-degree slope without incurring the rover actually being on that slope. We stay upright, which is better for control.
Yeah. One more thing to add real quick on that.
Yeah.
So the 15 degrees is our limit on the moon, on the lunar surface. Actually, for egressing from the lander, our limit is 30 degrees.
So those ramps.
Yeah, and the reason that we can go from 15 to 30, which is even steeper, obviously, is because it's an engineered surface. We know the interface, we know the materials, we know how they behave, we can test them exactly, and so it allows us to be more confident, and so there's no risk of tip over at 30 degrees, and as Emily said, we can use the suspension to not make the actual rover angle be 30 degrees as we're coming down the ramps.
Got it. We got some cool comments too coming in. Viper driver is a cool title. I agree. Yes. Awesome.
Thank you. I think so too.
Yes, we do agree with that. It's so cool to get behind the scenes. Thank you, NASA team. You're welcome. We're so excited to be able to be here today and show those exclusive behind-the-scene images. And good luck, Viper. Yeah.
I think we all
Thank
feel
you.
that. Yeah.
Yes.
We got another question from our audience as well. What can you tell us about the cameras that have been selected for the rover, specifically HAZ and NAV? You guys might know better than I do what that relates to.
We know. How do you know? Do you mind if I answer this one? We have. Can you hear me, the rover? We have a lot of cameras on our rover. Over here, this is our navigation unit. This one has 2 high-def cameras that can shine down. This entire navigation is also on a tilt and also a pan. So as Ryan mentioned, we can rotate to ensure the sun, you're my sun right now,
Thank you.
is charging our solar panels. But if our Earth is over there, we can rotate always to be able to talk to the Earth with our communication. Well, the navigation cameras are on that same independent rotating gimbal assembly, so that we could actually be looking over here when our rover is driving this way. So that's what we've used for navigation, and we have some high-powered lighting to help light our way. And then we also have hazard cameras. 2 of them are on the back part of the rover off of the aft solar panel here, because if we're driving backwards, for instance, so we have to evaluate what's behind the rover on this side. These cameras can't really see very well, so we utilize these. And then we have a camera on every single wheel not on the wheels, but monitoring the wheels so that we can evaluate risks that are immediate. We mainly use those while we're going off of our lander slopes, just to make sure we're not getting off the ramps. But we also use it for just hazard assessment.
Yeah.
How do you learn to become a rover driver? Because you all this knowledge you're saying it, I'm like, is it a video game? It's like, what's going? How did you practice and learn how to become one?
I'm still practicing. I'm still
that's
learning
awesome.
with
Yeah.
its continuous sims and exposure to the integrated system and how we work it
Sims?
out.
What is a sim?
Simulated missions.
Yeah.
Okay.
Basically, it's a software environment that we use
Got it.
to put ourselves in as much a flight-like experience as possible. So, and you use the same tools that we will be using on flight.
Right, so kind of like a video game, but everyone has their own consoles.
Yeah.
Our scientists have their own consoles of their simulated. We have to work together and talk to people. They could be right next to me, you sit just a few chairs down from the driver's station. But a lot of our scientists work out of a different, just room in the building, and then a lot of our team members work over at Houston as well. So communication, but it's all simulated for now. I think skills of playing video games certainly do help.
Did you like playing video games, or is that something that you?
The application had a few specific questions, like have you driven and operated a robotic vehicle without line of sight? So anyone the little RC car, and you can drive around, you kind of have this bird's eye view of everything. That's easier than it's in a completely different room, or you only have what the robot sees, that line of sight. Driving it without the line of sight is really big.
Yeah. And that's what it will be on the moon, right?
Yeah.
I mean, it's on another celestial body. So
and be able to see it.
yeah.
I've got a little bit of experience with field testing robotics. Back when I was in college, I deployed a little micro remotely controlled submarine in Antarctica. So I was on the top of the ice sheet, and this little robot was, several, not quite a kilometer down, but driving, I was completely tethered, utilizing only the camera and the lights from the little micro submarine. So it was very analogous to, going to space, just because your robot's in a completely different environment and you still have to control and navigate it.
Who knew that would prepare you for this? And I have to ask, I think it's roughly 10 drivers in total, right? You're one of 10.
Yes.
How did it feel finding out that you were selected? Was this college acceptance letter level? Was it winning an award?
Way bigger, way bigger.
This was way bigger. Not just a dream come true for me personally, but to be chosen to be in that ops team, to represent all of the hard work from the hundreds of people on VIPER. It's such a privilege to be able to stand there and be I've got you. I'm gonna take your work to the next level, represent all your hard work, and just keep going, keep pushing the mission.
Yep.
It's amazing.
Do you get goosebumps when you think about it? I get goosebumps.
Yeah. We got some questions about the live stream too. What are the cables connected to the engineers?
Yeah, that's a great question. We are dissipating any electrostatic forces that may happen. So, if you shuffle your feet on the carpet, you get a little bit of extra charge. All of our electronics are highly sensitive, so we want to make sure that we do not pose any risk to electrostatic discharge.
Yeah, essentially grounding them.
Safety first.
And their smocks, their white coats that they are wearing are also have a conductive thread that feeds it through. So all of those are electronic and grounded to the wearer as well, just so that we don't build up any additional charge on our personal clothing.
Right, and anytime you go into that clean room, you have to dress like that. Is that right?
Yeah, hairnet, bouffants, beard cover if you have a beard. They're very strict. No makeup, no jewelry, no as little skin showing as possible, because humans are kind of gross and we keep on shedding things, and we don't want that in our robot.
Makes sense. Yeah. We got another audience question. How big/wide is VIPER, and how will that fold up, or will it fold up to be able to fit on a rocket?
It's about 2 meters by 2 meters, but from the top of the mast to the bottom is about 8 meters. So it's pretty tall up to the top of the mast, but yeah, it's 2 meters by 2 meters. It's kind of like a golf cart size.
Right.
that kind of thing, that kind of shape.
It's big. I don't think, like, obviously this model's not doing it justice. You can kind of get the impression, I think, based on the live from the clean room, that it's bigger than a person for sure.
Yeah.
But even that's just the interior, right? So once it's got those solar panels and the mast on, it will be much, much bigger.
Yeah.
And
in the rocket, so it this obviously is not going to land itself on the moon. So there's a lander that VIPER gets attached to, which basically takes it. So the rocket will launch. The lander will separate from the launch vehicle. The lander takes the rover to the moon, lands on the surface, and deploys ramps. And we depart off the ramps. So the lander, which takes us there, it's a propulsive landing because the moon, no atmosphere like Mars has an atmosphere, so you can use things like parachutes and things. But on the moon, it's all propulsive. It's all rockets. So the lander has, it's much bigger than the rover. So the rover is actually not that big compared into what it needs to fit inside in the launch vehicle. The lander is the thing that takes up a whole lot more space. So we don't have to do anything. We're not designed to unfold or deploy anything. It's just as it is, as you see it here. It'll get mated to the lander, and the lander will take it, and then we egress.
yeah.
We have an audience question about the lander, so it's perfect segue into this question. How will the VIPER rover get integrated onto the Griffith lander?
Very carefully.
Yeah.
Very carefully. Yeah, I mean, you can see this operation is very cautious.
Yeah.
And it's just putting a panel, it's putting a panel, attaching it to other panels. When you have this whole integrated rover, things are going to be slow and methodical and careful and practiced. But in our configuration with the lander, we just sit on the top. Essentially, we sit. We're mated. We're attached. But so it'll be a lift operation basically, where we have the lander ready and the rover ready. Lift the rover up in the air and bring it over and carefully lower down. And our lander interface is fairly simple. By design, we wanted to make it pretty easy from a defining the interface point of view, and also just a mating and practicing point of view. So it's pretty simple interface. It's actually, I think the whole release mechanism of the rover and lander is really elegant for us. It's a cool design because you have to be attached, and you have to be attached very, very securely.
I'm sure.
But we're also, we also have some data and power coming through, so we have connectors, and so, severing that when we need to, once we're landed and we decide to egress, we actually do a kind of a wheel deployment and kind of a stand-up kind of maneuver.
Yeah, we've got like a few of these mating points from like the very bottom chassis of the rover that's mated to the Griffin, and then once it's time to deploy those, we sever those connections, and then the robot actually stands up because we have that active suspension. So the robot will stand up,
stretch.
Yeah, get ready for that.
Thought about that.
stretch, wake up, and then we'll power up systems and fully
cool.
egress.
Yeah, that's
So
awesome.
this rover is not going to fold up. It's just going to be on a lander that's designed for its size and in a rocket that's really big. Is what I'm getting.
You have to do it all carefully.
Of course, and it's all very careful, I'm
so
sure.
the lander is being provided by a Commercial Lunar Payload Services contract. So NASA basically said, we want to bring this rover to the moon. Commercial companies out there, can you bring us to the moon? And so they put out a proposal and get responses, and they evaluate. And Astrobotic in Pittsburgh was selected to carry VIPER to the moon. They're building the lander. It's the Griffin lander. So you can look up you look up the lander. They've got information out there. And you'll see it. I think they've got some images and stuff.
Oh yeah.
So you can see how big it is.
It's also sizable. Yeah. Everything on this mission is big.
We're getting awesome questions in the chat.
Yeah. I have one I think that might be good for Emily, but actually both of you probably can speak to this. So is the rover able to move around autonomously like an autopilot? Can it orient its solar panels, or is it all remotely controlled? So, as a driver.
It's all remotely controlled. Since the time delay just going from the Earth to the moon is so short, it gives us that ability to do all completely remote, direct drive, so to speak.
Yeah, it's not like Mars, right, where you have quite a long time delay. With the moon, it's not quite real time, but it's close.
It's close. I think our communication uplink and downlink kind of controls how many commands that we could send. But in terms of like the sims that we have and like developing that user interface for the software, which is amazing. We have like graphical interfaces that can like help you orient the robot. So we do that processing here down on Earth to give us that optimized drive to get like that. If you want to go say like 3 meters, we have software that will give like a recommended path in order to avoid hazards. It all goes through the humans, the drive team, the operator team to like approve it or make adjustments, and like some quick button tools to like snap the rover to get like the most power from those solar panels. So we do have that capability. It's just all here being processed on our side, so that when we send a command, it's just this is the final packet. It's been reviewed by us, but no autonomy on the rover.
Speaking of comms, we have a question. Could you describe your comm system and how it works not only on the south pole of the moon, but also inside of craters?
Yeah, so our communication system in the model here, Emily kind of spoke to this before, the antenna is here on the top, and it's on its own independent pan and tilt, so it can rotate full 360. Yeah.
Thank
That's
you.
a great
That's
visual.
a great
That's
demonstration.
an awesome visual of it.
And it'll essentially we need that pointed at the Earth, and so to be in communication with the rover, to be able to get the data and make decisions, see how the rover's doing, we have to have line of sight to Earth.
Yeah.
So
like when she was showing us the model, when it was pointed that way, it was intentional.
Yeah.
Yeah.
And on the south pole of the moon, the Earth is always low on the horizon. Like you can imagine, like on the Earth, if you're on the South Pole or North Pole, Antarctica or whatever, the sun's going to be low. And it's the same kind of geometry for the Earth's orientation on the moon. It's always South Pole's on the bottom. So the Earth will be low on the horizon. So it's kind of always pointed. So we generally be pointed as it kind of looks like here. And so we design our traverses to always have this line of sight. And so even when we go into a crater, or even a permanently shadowed crater, we've found craters that where we can go in and still have line of sight to the Earth. I said these permanently shadowed craters have not seen sun in billions of years. They do see the Earth.
They see the Earth,
They
yeah.
see the Earth. It's actually interesting because just like when we see the moon, you see reflection of the sun, right? That's what we see, the brightness of the moon. Actually, Earth does have some reflective nature to it too, not as much as the moon does, but it can still be bright, and so the Earth does illuminate in some of the portions of these permanently shadowed craters sometimes.
So you were in that. If you were in that crater, you would be seeing similar to
see
how
the
we see the moon.
Yeah,
you would
yeah.
be seeing. That's cool.
So we have to
seeing
see
the
Earth to be in communication. So
Got it.
so we design our traverses and our entries into craters and exit to always have line of sight. Now, there's a I don't know how deep we want to go. So the moon does a wobble.
A wobble, like
Yeah.
a dance.
It's a wobble.
Like a wobble.
So like it kind of goes like this, up and down like that. But it's a full month cycle. So it kind of, for 2 weeks it's kind of the South Pole's kind of facing Earth a little bit more, and then in 2 weeks it kind of rotates back. The Earth sets from the point of view of the pole, and it goes below the horizon. So we actually lose that line of sight every 2 weeks.
Oh,
And
wow.
so we, in a given month, one lunar day, we operate for about 2 weeks, and we get as much productivity and movement and collect as much data as we can, and then we find a good spot to hang out that doesn't have a lot of shadow period, and that's a unique thing about the South Pole. I could go on for another 10 minutes on that, but so we find a good spot to stay for 2 weeks when we're not in communications. And we pick these locations to minimize the amount of shadow period so that the rover doesn't freeze or run out of power. And then, once the Earth kind of rises again, we reestablish our communications and we do another 2 weeks. And we do about 3-4 months It's about a 100-day mission by design, and so we'll kind of have this kind of repeated pattern over the course of those months.
Wow, that's amazing. Like, just the different perspective of how you see the moon and Earth differently.
Oh yeah, I think Earth is even upside down from what we normally assume the Earth would look like,
Yeah,
but we
you're on
kind
the
of
South
have
Pole,
a
and
skewed
kinda-
view. Yeah.
Gotta
So if
reverse.
you're on the moon's South Pole and you're looking back at Earth, or what VIPER will be looking back at if it was, will be an upside down view of Earth. We have another good question. I think we kind of touched on this a little bit, but what will be the first task that the rover will be used for once it's deployed and tested?
Deployed, I assume, on the surface of the moon.
I would guess so.
Yes.
Yeah, I mean,
Okay. First task, drivers getting used to
is
driving
it that
on the moon.
stand up on the lander, or is it?
Yes, if we're, yes.
Yeah,
depending on when
after we
you're-
like stand up and egress, then we start going to our first science station.
Yeah,
correct?
we pretty much get going.
Yeah,
quick.
We've got like a few points of interest we call science stations. The goal is to get to as many science stations as we can. So once we egress off of the lander, we systems check out and everything, then we're gonna go for that science station. So I think the first tasks is, it prioritizes on driving, because to get to where the scientists want to go, so our sensors can get the most meaningful data. So it's going to be all about getting to those interesting points and then starting the survey. I don't know if we're doing any measurements or anything directly after the lander, but we could ask. I'm sure there is the right answer for this.
Yeah, primarily that first part of the mission. We want to collect as much data as we can when we're there, make the most of our time there. And there's a very dynamic lighting environment.
Right.
The shadows move around. It's not like, in the middle of the moon or the equator where, we see most of the time when you look up. It's like 2 weeks of light, right, and 2 weeks of dark. The South Pole is nothing like that. It's not a cycle that's repeatable like that. It depends on the terrain, because the sun is always low on the horizon, and it's very mountainous on the moon, and so you get shadows coming. It could be at any time. We obviously know that. We can model it, we can predict it, and we design our traverses to stay in the sun generally,
Right.
Until we actually want to go into a shadow. So we design our traverses, and so we just need to be moving, and so we usually we'll come off the lander. We're trying to check things out on the way to the moon, right after landing, egress, and we're hoping to be just ready to go.
Right,
We'll
not
of course deal
wasting
with
any
anything that
time.
comes up.
Right.
But
like
get straight to work.
And like the science happens, like those are actually harder places to land because of the lighting situation, because of like the slopes, and because like it being a permanently shadowed region. So we have to set the balance of having a safe place to land versus being at the interesting, like where the cool stuff is gonna happen.
Right.
So we're gonna try to balance that out, but that's why we'll have to do a traverse first.
Yeah.
That's awesome. Well, more about what more questions from our chat are. What are the temperature extremes the rover will face while on the moon?
Excellent question, and it's not a simple one to answer, because different materials have different optical properties. So, for instance, and I'm going to get into my MLI stuff because I know it. I have a lot of like the color white is what we use because it reflects a lot of the heat. So like if you have, say, a white material and a black material in the exact same spot on the moon, the black's going to get a lot hotter than the white does. And similarly, like when you go into like the cold factor, because it also reminds like how much the black will absorb that heat versus how much it's going to reflect it off. So at any given time, the temperatures across this rover will be different depending on the material, depending on the optics. So you don't have like a straight answer of saying, oh, well, we have to survive, down to 17 Kelvin because that's what the coldest, piece of rock that we think is at, and are in a permanently shadowed region, all the way up to 400 degrees Celsius, because that's what a different rock gets when it's in the sun. But it's like sorry to change units on you. I'm very aware of it from Kelvin to Celsius, and I apologize.
As long as you state the units, you're good.
But it's a difficult question to answer. I will say that we test all of our equipment with a lot of cycles of hot and cold.
A lot of
them-
preparation.
A lot of preparation.
Yeah,
Like I think like the part of the mobility units was tested as low as like down to negative 80 C and then like 120 C, like that kind of range for operations.
Yeah, the materials on the rover, they're designed to survive the temperatures that the materials will see, not what the environment sees, but we control the temperature of the rover, all parts of it, and either by passive design with MLI or with heaters to warm something up when we don't want it to get that cold. So we maintain the rover temperatures to make sure that it's going to survive, while the environment may be a lot hotter and colder, but obviously the environment has to be factored in when you understand how the rover is going to need to survive it.
Yeah.
Of course, yeah. We got another question about VIPER and its movement. What is the runtime for VIPER before it needs to stop and recharge?
Ooh, good question. I think it really depends on what we're doing. But as a driver, we always try to position our solar panels so that we're always getting electricity from the sun. So we have like a measurement that like if we are at an exact like 45-degree angle or a orthogonal to the sun rays, are we charging our batteries 100% or like 0%? And we don't like to do any operations that dips below like 90%. We always want to be at that higher end of charging. But obviously when we go into permanently shattered regions, we're going to be completely on battery. Well, maybe not completely, but very, very low sun absorption, if any. And I think that's going to be the question, right? I think we've got
We'll discharge the battery when we go into shadow, and then we'll come out and we'll have to recharge.
And I think we've got like 8 hours
Yeah, we've got
of
plenty of time.
operations. Now, me personally, I don't know how much of that is just pure driving and how much of that is science and a lot more higher processing. It all depends on what we're going to be doing.
Yeah, we can charge faster if we're not driving, just because we're not using as much power.
Right.
So like when we come out, if our battery state of charge is low, we may just kind of sit in the sun for a little bit
Yeah.
to get up to a comfortable place
I
where
like
then
to
we can start
recharge in
driving.
the sun as well.
Everybody does.
So, yeah.
Glad you and the rover have something in common.
I know, yeah.
So we have some comments too in the chat. Thank you for everyone who's dropping those comments in. I just wanted to say thanks, NASA. Science is the gift that keeps on giving. And thanks for pushing mankind to new frontiers.
And womankind.
Yes.
I like that.
I love that. And imagine working at NASA. How cool. It is pretty cool.
Agreed.
There are so many types of tape, guys. Oh my gosh. No, but it is a really, really cool and fun place to work.
All right, I think we have time for one more audience question. So let's see. I have one right here. Is the development of this mission going to be used in correlation with another mission, possibly any future missions? I think, Ryan, you touched on that briefly.
Yeah. So one of the findings that comes out of VIPER, just learning what's there and where it is and how much and how to get it, that can certainly inform future missions to use the resource. But also, it's kind of a reconnaissance mission. The Artemis mission which is coming up and landing people on the moon. They are going to the South Pole as well. That's their plan. They have landing sites that they put out a little while ago, and they're actually very similar. I think one of the landing sites was similar to our region where we're landing. So they're looking in very similar places. So we're going to go there. We're the first, to be in these areas, and we'll see what it's like. What's the lighting like? What's the lunar regolith like? How's the charging environment? I think just having a human kind of perspective on this place will help inform the Artemis missions, their plans, their designs, and just the living and working environment. So it's a lot of things. That's what's so cool about this mission. It's science, it's exploration, it's reconnaissance, and it's pathfinding somewhere where nobody's ever been before.
Yeah, it's a first. It's very, very exciting.
Yeah, historic. Well, we'll have two other VIPER experts joining us momentarily, but before we say goodbye to Ryan and Emily, there's a couple more comments I want to share. Yay, go science. Indeed a great show. Thank you so much for joining us. We're glad it's a great show, and this is so very educational. Thank you so much. So that, I think that shows how much we've learned. I know I've learned more about VIPER, and so excited to watch it come together.
It's together now.
It's on.
Yes,
So
look at
it's
that.
there. It's on.
It's
Is there going to
on.
be a top coming on top of that too? Is there a lid to this box?
There's definitely a lid to this box. It's coming back off. But we don't need the lid on for all of our power-up testing. So,
Got
yeah.
That's later.
That's
That's
later.
coming.
Yeah.
Another watch
A
party.
lot of good stuff to come.
Great.
Is there anything else that you want to tell us before you go? How does it feel working on such a historic mission? Are your friends, your family so excited for you?
Absolutely. Yeah. I want to touch on friends and family just for a little bit.
Yeah.
Because when the projects, had this call for like who wants to apply to be a driver, I was like, I apply, right? Like I apply, and my family was, and not just like my immediate family, but my friends and family, and my family support system was like, yes, you apply. I'm like, it's gonna be a lot of work. I've got 2 kids at home, and they're like, you apply. Like family doesn't hold you back. We push you forward. So I just wanted to say thank you, family and friends, especially
They're
my brother.
probably watching.
They better be watching.
Hi, Mom.
Yeah. How about for you, Ryan? I know this mission is long hours. It's
Yeah.
a lot of work. It's
Yeah.
years in the
Yeah,
making.
I've been working on this for probably about 10 years. So
Wow.
yeah, it's a lot of time and effort. Family is always supportive. Yeah, and they, I love sharing with them what we're doing and getting close to launching. So yeah, everybody's excited. And I'm excited too.
Same. Yeah. Thank you both so much for
Yeah,
being with us
thank you.
today. We're going to be sharing a live clean room shot with you while we let our other VIPER experts join us here in the studio. So stick with us. For those who are just joining us, this is NASA's VIPER Moon Rover Robot Build Watch Party. VIPER is NASA's first robotic moon rover. It has a 100-day mission and is scheduled to launch in late 2024 and land at Mons Mouton, a lunar mountain near the moon's south pole, which was named after NASA mathematician Melba Mouton. VIPER's findings will teach us more about the origins and distribution of water and other resources at the moon, and can help inform future Artemis crewed missions. You're currently seeing live views of our moon rover as it's being built in the clean room at NASA's Johnson Space Center in Houston, Texas. We're coming to you live from NASA's Ames Research Center in Silicon Valley, California, the home of VIPER mission operations. If you have questions for our experts that you'd like to see answered live, now's your chance to put them in the chat. We'll do our best to take as many as we can. All right, welcome you guys. We're so happy to have you here. Thank you for joining us on our second half of our watch party.
Thanks, Laura. The watch party. Why don't we start with some introductions? Amanda, why don't we start with you?
Sure. My name is Amanda Cook. I'm the integration and test lead on one of our payload instruments called NERVOS. I can break that acronym down for you later, but what integration and test means is that I'm in charge of the team that puts together our science instrument from its tiniest parts and electrical boards until it becomes a full functioning instrument. And then, we put it through its paces and then introduce it to the extreme environments of the moon to make sure it functions as we expect. And so that's the integration and test part of my job. But now that the hardware is delivered on this rover that you'll see in the clean room, my job has sort of switched over to leading the operations, the mission control operation of our instrument, to command it from the Earth to tell it what to do on the moon. So we send commands from the Earth and say, measure this, measure that. So now we're getting into that exciting part of the VIPER phase. So
Cool. That's
Very
so
exciting.
Cool. Yeah.
And Loretta, how about you?
Well, my name's Loretta Falcone, and I lead the mission planning team. In mission planning, we look at what the rover will do and where it will go. And together that builds the mission plan. So we will be executing the calibrations of the nervous instrument, all the instruments. We'll be looking at interesting parts of the mission, like science stations and drilling, and we are challenged by the light and the calm shadows at the moon, at the South Pole in particular, that really make this a dynamic project.
Absolutely. And I'm glad you mentioned the instruments, because we've got 4 instruments going on VIPER. We can't quite see them in the live views from the clean room because they're kind of covered up by those panels and all of the other hardware. But what can you tell us about those instruments?
yeah, sure. So as you said, they're kind of buried down in the rover here, and you can see they actually, most of them kind of point out of what we call the belly pan of the rover. So you imagine the rover has like a little belly, and
Inward here,
yeah,
correct?
on
Like,
the bottom,
on the bottom.
on the bottom surface of the
Okay,
rover.
got it.
So all of the instruments are already kind of packed down in there because they look through the bottom. So the instrument that I work on is called NERVOUS, and it's a silly acronym.
It's my favorite
I was
NASA
gonna say, it's her
acronym.
favorite acronym.
I love it, and I can
Talk
never
about it,
remember
yeah.
what it stands for, so
Yeah.
I'm going to have you do the honors.
Yeah, so it stands for Near Infrared Volatiles Spectrometer System. And so as the name implies, it searches for volatiles, and the V is the same as the V in VIPER. So volatiles are substances that are, you can kind of think of them as ices. So things that, if you just give them a little heat, they kind of turn into gas. That's what volatile means. You know, it gets shaken and, you know, gets volatile and turns into gas. So it includes stuff like water, CO2, ammonia. And so our spectrometer system points at the lunar regolith as we're kind of traversing along, and we measure the composition of the surface as we're moving along. And NERVOUS also takes images of our path as we move along, and we also measure the surface temperature. Now, there's another instrument called M-SOLO that is a mass.
My favorite acronym.
Yeah, right. M-SOLO, yeah, very like
M-SOLO.
space
That's
nerdy.
right.
Yeah,
Thank you.
definitely a nerd reference. So it's called a mass spectrometer system, and what it does is it kind of sniffs the surface. So it's kind of sucking up gas that is coming off the surface and passing that gas through, you know, some tubes and measuring what the composition of those gases are. So similarly, measuring volatiles. And then we've got the instrument, the neutron spectrometer system, which you can kind of see pointing out the front here of the rover. And you can sort of imagine that as like sort of like a laser gun, like wow, wow. It's like pointing into the surface of the moon, and it can sense water beneath the surface. So it's kind of our first indicator of where the water is. So that thing is kind of moving forward and measuring, like, is there going to be water underneath the soil here? And so that's what the neutron spectrometer system does. And then lastly, there's the Trident drill. And you can kind of see it, you know, poking out the top of the rover here.
Right.
Right.
And the Trident drill, you know, as Ryan mentioned before, you know, goes down into the surface about a meter deep, and then kind of pulls out regolith bite by bite and kind of dumps it in front of all the instruments. So we can watch individual bites get kind of dumped in a pile on the surface, and we measure the stuff that's on the pile.
Wow, that's pretty cool.
Yeah, so Trident is really cool too. Enables a lot of really interesting science for VIPER.
That's amazing. VIPER's going to be doing a lot.
Yeah. Driving, moving.
Yeah, drilling. Yeah.
Drilling. It's a lot of things that are happening.
So what kind of data are we expecting to get back?
You want me to take that one? Yeah. So we are essentially kind of mapping the moon, the South Pole at our landing site. And the idea is that we kind of want to understand what is the distribution of particularly water at the South Pole. You know, we do have orbital measurements that show us in these permanently shadowed craters, we're sensing water there from orbit for sure, but we want to get down on the ground and say, okay, well, like exactly where is it and how much of it is there? So the rover actually generates a map in real time
Really cool.
of its path, and we can say, you know, as we go along the path, there's a lot of water here, a little bit of water there, not so much water here. And so we kind of generate that map with, you know, laterally on the surface, but also with depth. You know, is the water 30 centimeters down, or is it, you know, 90 centimeters down, or is it right, you know, a frost right at the surface? So that's kind of the data in a you know 30,000 foot view that we're looking
Getting
to get.
the map.
Yes.
Yes.
Yeah.
Yes.
Ideally, we would be able to correlate that with the orbital maps and be able to predict from this mission and these mission results where will we find water.
Right.
Yeah.
Yeah.
That's fascinating.
And we're building on, if I'm not mistaken, some previous lunar missions that have already given us a sense of what might be there. Is that right?
Yeah. Predecessors from Ames, right?
That's right.
Yeah. So you want to talk about LCROSS?
Go ahead.
Okay,
You're
sure.
on.
So
Another acronym though?
yeah, oh my goodness, LCROSS, and I have to remember this acronym because I wasn't on that mission. So Lunar Crater Observing, I don't know.
Yeah.
That's all right.
I remember. Anyway, it was a mission that came out of NASA Ames too. But this one was super cool. You know, it came on a rocket, and the rocket was basically ejected a little projectile, and it crashed intentionally crashed into a crater on the moon, at the South Pole of the moon. And then the satellite, as it passed by, made measurements of the ejecta plume that kind of burst out of that impact. And what we detected in that ejecta plume was a ton of water, like way more than we expected. So that was like, you know, we kind of go from the orbital data where we're like, you know, seeing stuff on the surface, and then you go to this like, okay, well, let's explode some of it up so we can see, you know,
What else?
what else we see.
Yeah.
And now we're going to kind of get like down and dirty and really see, you know, close up what the water looks like. So
Very cool.
Yeah.
I know we're very excited to see what happens.
So this mission, what makes this different? This rover different from Mars rovers?
yeah.
Oh, that's a great question. So there are so many differences. Well, one is this mission occurs at the South Pole. And we have one mission, I believe at Mars, called Phoenix, that went rather south, but not as south as this one. Boy, we are 90 miles from the South Pole of the moon. And, you know, as it is on Earth, when you go very far north or very far south, you know, the sun doesn't rise. I'm sure in Scotland right now, the sun is very low in the sky, and they're the kinds of issues we're also finding on our lunar mission, and that makes it just so difficult to plan as well.
Everything's got to be very precise.
Very precise, because we have the shadows for both light and calm that converge. And they create these bottlenecks of areas for us to traverse. So what causes these shadows is something called lunar libration, and it's kind of like a little shimmy. So
A moon shimmy?
a little lunar shimmy. Yeah. We can see 50% of the disk at all times, but we are able to access 59% of the surface of the moon, and that's where our mission area is located. There we are. There's our mission area. But I want you to see that if you are the Earth and you need to communicate with that small little area, that area will become apparent for 2 weeks. and it'll come down for 2 weeks. And these are the areas where we conduct our mission. So we conduct our mission just where we can communicate. And then it fades away. And during those times when it fades away, we need to be in a place that's relatively warm, so there are a few spots that are high enough so that the rover can stay in the sun and stay warm till we have calm again.
Well, we have a great comment in the chat that says, "Hi from Scotland. Can confirm low sun." Thank you, Scotland, for the
Thank you,
confirmation.
Scotland.
I appreciate that. So great analogy and explaining that over to us.
Yeah.
Absolutely. And I mean, you've been talking about some of the challenges and some of the communications. What are we actually using in order to communicate with the rover? How do we communicate with something on the moon?
Well, we use the Deep Space Network. The Deep Space Network, and that's fascinating. Fascinating difference between the moon and Mars is that the Deep Space Network for our mission will be directly pointed to the moon. And for Mars, it's actually, the commands are sent up to a relay satellite, and the satellite will send those commands back to the rover on Mars. So that means that we always need to be in comm with the DSN.
Yeah, there's no relay at the moon.
Not yet.
We just got to point straight at the Earth to get our data there. Yep.
That's awesome.
Yes, yes.
We're getting some great questions for Loretta and Amanda, so thank you so much. Keep them coming. Amanda, this one's for you. What went into designing Trident, and why a drill?
Oh wow! So Trident is actually designed and built by one of our kind of vendor partners that NASA works with a lot, Honeybee Robotics. So they are experts at drilling. They do the long drills, the short drills, the percussion drills. They got all the drills. So one of the things that was considered in the design of that drill is that on the drill stem, there's two different kinds of, you might call them threads. You know, it looks like a screw basically. And on the very bottom 10 centimeters of that drill, the threads become very flat. Whereas at the top, you know, from the middle to the top, they're very slanted like you'd see on a screw. The reason that they're flat at the bottom, flatter, is that we want the drill to grab material and hold that dirt on the flat pieces of the threads so that it doesn't just slide off on those slopey bits, right? So on those flat pieces, the dirt is gathering and then the drill pulls up, and it's cool, there's like a little brush. The drill passes by this passive brush that just kind of brushes off that material from the flat parts, and that's when it dumps it into our pile. So that's one of the cool design elements of the drill.
And when you said that, I was thinking about, you know, that game that you play at the pizza parlor where you're grabbing the claw and you pull like the stuffed animal. And so when you said that, I thought, okay, so the drill, it's not gonna let go of that.
Yeah,
it's holding on to that.
Holding the dirt, yeah.
That's the visual image I
exactly.
got. Yeah, that's awesome.
Very cool. We also have a question specifically about the Nervous instrument.
Oh boy.
So how long is the process of Nervous identifying the nature of the hydrogen in the lunar soil and then communicating the findings back?
Oh yeah, so how quick do we need to let you know what we're finding, right? Yeah, I think, you know, we engage with the public as quickly as we can. And, you know, the rover, Nervous actually starts collecting data before we even get onto the ramps off the lander.
Oh.
Wow.
So
right when you get there?
yeah,
essentially?
pretty much right when we
Wow.
get there, the rover kind of gets like released. It's like a little pop off the lander, and then it starts to rove down the ramps. And, you know, we expect with Nervous to be looking at the regolith immediately. We're not going to know right away exactly what we're looking at. What we will do is measure the mineralogy, and our technique in general is to kind of measure changes in the water concentration. So, you know, I'm not sure exactly how quickly that information gets out, but my guess is, you know, within a week or two, we would probably be releasing what NASA calls our science nuggets. So our little kind of brief, packages of what we've learned so far. So I would expect that first data to come out within the first, 2 to 4 weeks of the mission.
Wow.
Yeah, as quick as we can.
Yeah, you can imagine how excited we'll be when we first find water.
Yeah, it's going to be a moment for sure.
Well, it's interesting that you're talking about those little nuggets piece of information, because one of the questions I was asked, what specifically are they looking for in the soil samples? Is there anything you're looking for in that?
Yeah. Yeah. So, we're looking for water, of course. I've said that a bajillion times already. But we're looking for other volatile materials, CO2. A lot of this comes down to more of the sort of science aspects of VIPER. So, VIPER is a prospecting mission whose main goal is really to kind of search for water and understand water concentration. But we're there, and we have this opportunity to learn a whole bunch of other stuff about the moon. So how did the ice get there? What kind of ices are down there? So we will be, measuring all sorts of different. Can you remind me exactly? I kind of went off on my little spiel.
It's totally fine.
Yeah.
We're so engaged. We don't know the question anymore.
We're so engaged. I'm sure our viewers are loving it too. The question is, what are you specifically looking for in the soil samples?
I think I kind of covered that. There's a bunch of different volatiles. There's some mineralogy that we'd like to cover.
Yeah.
What is the age of the material that we're looking at? How did the moon form?
Yeah.
So what's the comet impact history?
Yeah.
You got me started.
It's okay. We're learning. We're enjoying it.
Yeah, and I know we mentioned water. We don't know exactly what we'll find, but one of our questions is, say we do find a lot of water on the moon, what happens next? What do we do then?
Ooh, that's going to be really exciting, because this is, we are looking to map out our in situ resources. So how deep is the water? We think that it'll be relatively more feasible to harvest water at 1 meter depth, and that's why the length of our drill is about 1 meter. So how will we harvest water in the future? How will we create fuel from the water? All of these plans are being explored by different parts of NASA and different collaborators with NASA, and this is really laying out, if we can find and map out the resources of water and hydroxyls on the moon, it will enable all the future missions. That's why this mission is so terribly important.
Yep.
Well, we got some great comments in the chat as well. Thank you guys. Y'all are so awesome. Welcome.
You're
Thank you.
awesome.
Thank you, right? You're awesome. Love to see all the women here. Yay.
Yeah.
Yay.
Yeah.
Yes, women in science.
Yes.
VIPER Moon Rover sounds awesome. Looks like a lot of hard work. And thanks for the build party. Fun, informative, cozy. Please have more of these.
Awesome.
So thank you. You're welcome. Love learning from our subject matter experts.
Absolutely. And I know you kind of just touched on this, Loretta. Another question from our audience, is there a long-term, big picture reason why we're exploring the moon again? So I think you mentioned this could really pave the way for future missions. Is there anything that also made you want to do a lunar mission?
Oh my gosh, yes, of course. I'm a child of Apollo. And as I was growing up, everything was about the moon. There were advertisements. Our school education had changed after Sputnik was launched, so I learned a kind of mathematics that was set theory and nothing arithmetic. And so I was groomed at a very young age to go to the moon, and they would tell me, hey, you can go to the moon. So coming from the Apollo generation, there's more to drinking Tang. It was really embedded in my heart and part of a passion and a love to go back to the moon. But when I started working for NASA, there weren't any jobs available at the moon, so I had to start at Jupiter. And so it's really nice to come back home.
Darn.
Just old Jupiter.
It's wonderful to come back home and be in the hood and hang out and look at the wonder that has been with us all our lives.
Yeah, I mean, it's incredible. The moon, you can see it almost every day when you go outside.
so.
Yeah, unless it's a new moon, you know? So yeah, I mean, it's our closest celestial neighbor. It must be so exciting to be able to see it and then know that you're working on something that's going there.
Yeah, yeah.
And
It
we're
is,
seeing
it
it
is.
being built in front of us.
Yeah.
This is a really exciting time.
Yeah, we're blessed. We're very grateful to be here.
Yeah, and one of the other things I wanted to mention is, you know, the moon is like a stopping point for going to Mars. You know, they talked about this a little bit, Ryan and Emily, but you know, the gravity at the moon is 1/6 of the gravity at Earth. So if we can bring stuff to the moon, harvest resources from the moon, and then launch to Mars from the moon, it's a lot less expensive because escaping the moon's gravity is a lot easier than it is from the Earth. So you can kind of think of the moon as the stopping point, you know, the bus stop on the way to Mars. So that is kind of, you know, NASA has this Moon to Mars program.
And there's so much that we need to test all the time. Right now, we're running our simulations, and it's interesting how many little bugs pop up out of just the instrument, even our procedures, and I'm sure that will be a proving ground for us at the moon before we get to Mars.
So are you running tests here at Ames? Like, what does that look like? What's day-to-day for you look like?
Yeah, isn't that interesting? So as the astronauts run through simulations, you know, we've seen videos of them working underwater to exemplify what they'll actually be doing when they do their spacewalk. Well, we do that at our lab and mission control here at Ames. This mission will be operated from the Ames Research Center, and we're going through all those procedures right now.
It's a lot, right?
It's a lot.
Yeah.
It's a lot.
But we don't have to be underwater.
No.
That's a good thing.
And our operations team is huge too. We have, you know, the people we call in the upstairs who drive the rover, operate the instruments, and that's, what is it, like 30 people up there. And then we have the science center where all the scientists are interacting in real time, looking at the science, saying, oh, that's interesting, can you measure that again? Or so they're kind of talking directly up to us upstairs. So down there they've got, you know, I think 15 people at a time. Wow. So there's a ton of people to try to organize and interact with effectively. So we're practicing that. It is no simple task, but we're learning a lot. We're learning.
Well, you got a fan out there because it says Amanda's a rock star in the chat.
Oh.
So thank you. Awesome.
We agree.
It's a plant. That's a plant for sure.
A family member? Did you arrange?
What does it look like for you day to day, like as you're building this?
Yeah,
A rock star?
Yeah, right. I break out my guitar in the morning and sing a space song. No, it's really it's a great job. You know, one of the you know, it's kind of cheesy, but one of the greatest things about working here is the people, right? Because everybody's got this passion that, I mean, you are one of my favorites. Like, just people have this real passion for being here. And so I interact with lots of people every day. And, you know, I have meetings like people. I'm, you know, on these video calls and taking notes, and sometimes it's a little jobby. Yeah. But, you know, like last week I got to go out to JSC, Johnson, where they're building the rover. Yeah. And got to, you know, run some early tests with the Trident drill to kind of...
Did you do the test in the clean room? Or
no, we were doing it with
like
the engineering hardware first, because we're practicing there before we do it on the real thing. So very, very careful. Yes. So basically, we were practicing this part of the mission where the nervous instrument is watching the Trident drill go down, watching it descend to the surface. And so we sort of take like a little video as the drill kind of descends into our field of view and then sort of squishes into the lunar regolith.
Yeah.
So, you know, running those kinds of tests is really fun. I tend to be running tests all the time, operating the instrument, and then participating in these mission op sims like once a month or something
Yeah.
like that for a
Yeah.
week of overload. And so,
That must be exciting to be doing that and to
Oh,
be
for
running
sure.
text. Yeah.
yeah.
It's interesting what a culture of humility
Mm.
there is in our mission team and in our operations. You know, it's so important to work together. You wouldn't imagine what a social concept this is. If you would imagine an engineer or scientist working at NASA, you might think, oh, I'm nerding out. But it's actually, we're all talking and communicating because we're all sort of experts, subject matter experts in our field, but it's so important to relay, hey, no, this is really important. This one's got to go to the top. We need to clean this idea out. And it's so important to ask questions. And these are all things that, you know, we learn as we're educating ourselves, as we're growing up. And the process of asking questions, being humble enough to say, Donna, what do you think?
I don't
You
know.
got it?
You
Yeah?
know? we
gotta
figure it
figure it
out.
out.
Yeah.
Yeah. Well, that's when you're
Yeah.
working on firsts. You don't
Yeah.
always know until you do
don't,
it.
Yeah.
You don't, and that makes it so much more fun.
Yeah.
You know, the whole passion of discovery.
Absolutely.
And part of the feel of being an innovation, right? Where you're not always going to know, but that's
Gotta be
why we're
brave.
testing.
Yeah.
That's why we're learning.
Yep.
You know that you can figure it out, even if you don't have all the tools you need at that moment.
Well, and again, your fan has said, I want a copy of the space song.
Oh, right. It's terrible.
Yeah.
I'm sure the lyrics are probably very unimaginative.
Thank you for all the great comments in the chat.
Really good comments.
Yeah,
We're
it's
getting
great
great
feedback.
questions too. This one came in, what will happen to the rover once the mission has been accomplished? We know it's about 100 days, so
Yeah.
what's the plan
Yeah.
after the plan?
Well, the plan after the plan, the poor rovers are going to freeze. Because as we said, it's going to get dark. We won't be in communication with the rover, and the rover will get very cold. We have thought about maybe some innovative ways to save the rover, but we're not sure how those will materialize. But it'll be, you know, in the relics of the museums of all of our Apollo missions.
Yeah, our
Yeah.
moon museums on
Our
the
moon
moon.
museums.
Right, it's
Yeah.
going to stay where it ends.
Yeah.
Yes, right.
Incredible.
Yeah.
Well, I think you triggered some great questions too, Loretta, about the moon. Is there a long-term, big picture reason for why we are exploring the moon again?
Yes, to explore the resources and to enable missions to the moon. I think to harvest the resources would be one, and really as a starting point for Mars, for our further exploration, as a mission proving point for Mars.
Yeah.
Well, did you ever think you were work on a lunar mission while you were discovering the Apollo age? Or growing up in the Apollo age?
Really, it was my dream. I did. I thought I'd be here.
And you did it.
That's great. I love that,
I
that
love that.
confidence and that
Yeah.
boost. I did. How about you, Amanda? Did you ever think?
Yeah, I didn't think I was going to be working on the moon, but I mean, you know, not
For the
On the moon,
Hey,
but
you might one day be working on the actual
maybe.
moon. Yeah.
I was an astronomy student. So I was, you know, I've always been into the stars and space and human exploration as just this kind of like, I don't know, metaphysical, you know, just like pursuit. So it's fascinated me from a very young age, and I knew going into college that that's what I wanted to study astronomy. And then, I came to NASA, and there were just all of these really cool projects, and I started to realize that, you know, I'm a teamwork person. And
Collaboration,
So,
that's
so these like kind of large mission teams have really like scratched that itch for me. I get a little bit of the science, the exploration, and, you know, the social interaction with other passionate people. So, yeah. I didn't know, but I'm super glad I'm here.
We're glad you're here too.
Yeah.
I wanted to also ask you guys both, What aspect of the mission are you most excited about? We saw Ryan and Emily getting really excited about this heat spreader panel getting installed. I don't know that that's their
And about
mission
tape.
high, but what are you most excited about seeing? Will it be the complete rover? Is it the process?
Finding water?
So whatever we find on the moon.
Yeah, getting the results of the mission back, achieving mission success, surviving these very challenging environmental conditions, and you know, sharing the accomplishment of getting it done. It's beautiful.
Yeah, I mean, similar for me, I guess. We've done a couple of experiments with earlier versions of this rover where we will, you know, drive it around outside in like a rock yard. And, you know, we've experienced in some of those tests that we will rove over something that we were not expecting to see, and everybody will kind of like throw their hands up in the air and say, paperclip, like we rolled over a paperclip. And it's just funny that, you know, even in that moment, looking at Earth dirt, that we could get so excited together. I just can't even imagine what it's going to be like on the moon when we see something that just we didn't expect. I'm so excited to like share in that thrill with these people that we've been working with for so long. So
And that's just the testing part of it. We were getting
excited. We were just looking
imagine
at
the real deal.
Exactly. What Emily said earlier, like the goosebumps that she feels.
Yeah.
And that piece of it. So it's so exciting.
Do either of you have any advice for people who are also envisioning themselves working on the moon one day, how to get to NASA or how to get to a mission like this?
Yes. To focus on the process as well as the goals. It's funny, we've made our lives so sort of goal-oriented, but a lot of times you can't always get to that goal when you imagine, like life just gives you this zigzag path, and it's really what you're learning as you're exploring something or as you're learning something. You can feel like a tunnel of darkness, but it's not too far from through that tunnel of misunderstanding or confusion that you get, that big aha, and then you walk back in and look back like, why was I so confused about that? And we all experience that, even as scientists and engineers. We all struggle through different concepts. So harnessing in on those difficult points and putting them under your wing and going, all right, another one, figured it out, and move on to the next class, the next project, and to know bit by bit you'll get there.
It's beautiful advice and a sense of keep moving forward in the process even when it gets hard.
I guess what I would say is don't be intimidated. You know, I was a good student, but I wasn't like the top student. And I was just persistent and stubborn. You know, it's not as difficult to work for NASA as it might seem. And you can come from a whole range of areas, whether, you know, obvious ones, science and engineering, right? But there's a whole bunch of different ways to contribute to NASA's goals, and they expand, you know, out into procurement, and of course NASA has HR, and you have, you know, special ways to support scientists and engineers. So there's so many ways to contribute. So yeah, don't be intimidated. That's my advice. It's like, if you want to be here, you can be here. So
Yeah, we're bringing humanity back to the moon.
Fantastic.
No, that's great advice. I think with all of our guests today, we've seen such a range of different types of work that you can do and different ways that you can get to the agency. So
Creative work, seamstress.
right.
Yeah. And it's interesting how important that artistic perspective is, because so much of our work is imagining what it would be like and looking for creative solutions. It's not like you can study the solution and just implement it at NASA. It's all like the first time we're doing something for the
you got to be creative.
Takes a lot of imagination.
Well, thank you guys so much for being with us today. I'm so sad that we're got to say goodbye at some point, but thank you both. Thank you also to Ryan and Emily, who were with us earlier, for just watching the stream with us, hanging out, answering questions. And thank you to our audience as well. Thank you so much for the comments and the questions you've been sending in.
And you can continue to learn more about the VIPER mission by checking out our webpage at nasa.gov/VIPER.
You can also follow by following along on social media, following at NASA Ames for the latest VIPER mission milestones and updates. Thank you guys so much, and
Go
hope you come
VIPER!
next time.
At Astra.